Hi, I'm Linda Gaines, and I'm Transportation Systems Analyst at Argonne National Laboratory. And I've been looking at battery second use and also battery recycling for the Department of Energy. And I'm going to tell you a little bit about the work at the Resell Center on these topics. So the first thing you need to understand is that used electric vehicle batteries are actually still quite useful. They get taken out of service in the vehicle not because they're dead, but because they just don't have as much power. And so, for instance, your 100-mile range Leaf might only go 60 or 70 miles, and that makes it much less desirable for your vehicle. But this battery still can be used, for instance, to store power at an electric vehicle charging station where mass is not a big issue. If you if you have to use a little bit more weight of batteries to power the charging station, that's not a big problem. So this is an example of a Japanese 7-Eleven where used batteries have been stacked up to store power from a solar-powered charging station. And that's one kind of use that the Clean Cities program could certainly make use of for used electric vehicle batteries. Here's another. This one is used Tesla batteries that are being used to power a tourist vessel in Sweden, but it only has to be charged once a day, and it works quite well. It's quiet, and so that's another kind of use that you could have for these used batteries. So they're quite powerful and usable. They just aren't as good as you would want in your vehicle. Here's another example of a company that plans for its whole battery's life cycle. Proterra is a U.S. bus company, and they purchase cells from LG Chem, and they construct them into battery packs using a standardized module that they design, and that's important, and a flexible battery management system. They then put them in buses, which they lease, and when the battery gets to be not as powerful as you'd want it to be to run the whole bus route, they take them back. And because they've made the system flexible, they can reconfigure the modules easily and cheaply into charging stations, and they can even use those charging stations to charge more buses. In addition, they've gone the extra mile on this, and they've contracted with a battery recycler so that at the end of the battery's life, when it really doesn't even have enough charge left to be able to run the charging station, they can actually recycle the material. So that's sort of an ideal life cycle. There are pros and cons of using the battery again. The obvious pro is that you've already paid for it, and it's a powerful little battery, and you can get some more use out of it. And the more use you get out of any device, the fewer resources are consumed for each use. And once you've sunk the cost in this, you might as well use it. But on the other hand, it really isn't as powerful as a new battery would be. You don't know how long it's going to last, so you probably wouldn't want to spend too much if you were buying it. And in fact, testing it and reconfiguring it, if you haven't had done some standardization the way Proterra did, costs money. It takes time, takes labor. You might need a new battery management system to run the different use, and that isn't cheap either. And the kicker on this is that the costs of batteries have been going down and down and down. So by the time this battery is ready for second use, new batteries may be just as cheap. And why would you use an old one if you can get a new one for the same cost? So although used electric vehicle batteries can find high value uses, and these can be cascaded, where first you use it in a car that's battery died for some reason, and then you can use it in a stationary use like the 7-Eleven. But eventually it's going to need recycling, and the Resell Center's mission starts when it does need recycling. The Department of Energy has a 3-part plan for dealing with critical materials, such as the ones in electric vehicle batteries. One of these is to reduce the amount of cobalt and now nickel in the batteries so that we don't have to import these materials from other countries and have more energy security for ourselves. Another is the Resell Center, which is composed of 3 national labs, of which Oregon is the lead lab, and also 3 universities. And our mission is to develop an economically feasible battery recycling process to keep the materials in circulation and hopefully in this country. The last part of that is the battery recycling prize. And the idea of that is there are lots of batteries, and we at the center are learning how to recycle them, but they won't get recycled unless somebody figures out how to collect them and get them all to a center. So that's what the third part of DOE's plan is. You might want to know what happens to the batteries now. Well, electric vehicle batteries really haven't come back yet, but EVs haven't been in service long enough, and so there isn't an established pathway. The hope is that electric vehicle batteries will just go along with the vehicle, and there'll be some way to collect the batteries at an automobile recycling yard. Consumer electronics batteries are a whole other thing because everybody's got bunches of them all over the place. They're in your earphones and your phone, and everything has batteries in it. If you have an old phone, you may not turn it in to get it recycled or reused. You may have it in your drawer. So there's in fact a stockpile of old electronics that is in people's houses. Sometimes these things do end up in the garbage, and that's a problem. There have been fires that the batteries in these devices have caused in municipal waste, and so that's the EPA, in fact, is running a series of meetings to try to figure out how that should not happen. And that's also another really good reason to make sure that the projects in the battery recycling prize are successful. I mean, not only do we get the batteries back, but we keep them from setting fires in the garbage. There are also a lot of batteries that end up being exported. A lot of old telephones and computers and things like that are exported at the end of their useful lives in the US. So if you want to understand how to recycle a lithium-ion battery, you need to have a little bit of understanding of how you make it in the first place. As with almost anything, you start with materials in the ground up in the upper left of the slide there, and you refine them going down the blue line, and then you make them into specialized chemicals that you put into the battery. In particular, the cathode is the positive electrode, and it's the most valuable part of the battery, including a very interesting, complicated crystal structure that gives it its properties. You take the cathode, put it into a battery, and you use it. The end of the battery's life, you probably want to take the battery and chop it up into smaller pieces to make it less hazardous, because batteries have voltage in them, and transporting them is expensive because they're in fact classified as hazardous materials by, I'm not sure by whom actually. Anyway, once you've got these end-of-life batteries, they can go through 3 different types of recycling. Pyrometallurgical processing is essentially throwing it into a big furnace where everything melts or burns, and so it's treating the end-of-life battery as if it were ore. Hydrometallurgical processing is a little more sophisticated. You dissolve the battery pieces in strong acid and then spend a lot of energy and time to separate the different ions in the solution from each other, and then make it back into the materials that can go into a battery. Direct recycling is the third way that you can conceptually recycle these batteries. And we're recovering the materials in the battery with their complicated crystal structure intact, so that we don't have to redo all of the energy and material and labor intensive process steps to get to the battery material. This picture shows a typical high temperature furnace. It's not actually a recycling smelter, but that's pretty much what it looks like. And I'm showing this to show a basic flow chart of what the process looks like. The key piece here I put in red, and that's the aluminum and the lithium that are being lost to the slag. The aluminum is, in fact, one of the very energy-intensive parts of the battery, so losing that is really a problem. And lithium has potential scarcity issues, so we don't really want to lose that either. For hydrometallurgy, you don't actually have to lose any of the materials, but it does break the crystals up into little bits. The aluminum and the copper are recovered right at the beginning after shredding. There's a whole set of chemical reactions that are undergone to get you back to precursors for the cathode and then the cathode and other materials. But there are problems, potential problems that you have to avoid when you're dealing with so much strong acid. And so there are environmental concerns about this kind of processing. With direct recycling, again, the key point is not breaking down the crystal structure into its chemical components. But there are challenges as well as benefits to this kind of recycling. One is that the material that we're recovering is whatever was in the battery when it got made. And electric vehicle batteries are likely to last 10 or 15 years. And as you may know, the cathode chemistry and other parts of the battery as well have been evolving over time. And so one of the things that we need to do when we recover material is upgrade it to make it compatible with the newest forms of the materials. In addition, we have to make sure that the material has as high a standard of performance as the new material that it would be replacing. And the real disadvantage at this point is that nobody's done this on an industrial scale, and people are unwilling to invest in something that hasn't really been tried and proven. And I've just shown this one to give you an idea of how complicated the crystal structure that we're trying to maintain is. And that's that structure way on the right. The little green balls in the right-hand crystal structure are the lithiums that flow in and out and back and forth when you're charging and discharging the battery. And in fact, one of the problems with used batteries is that some of those lithiums have gotten stuck elsewhere and are no longer available. So one of the important processes that we're doing in our experiments is learning how to actually restore that lithium. The other simpler crystal structures are the kinds of things that you would get back from pyro or hydro. And this slide gives you an example of the kind of complexity in each layer of a lithium-ion cell. And in particular, the most valuable piece that we're trying to get back is that cathode, which even once we've separated it from the other components of the cell, is not a simple material. It includes a gluey binder material to hold it together and to the aluminum current collector, some carbon black to make sure that it has sufficient conductivity. The way we evaluate all of our processes is with life cycle analysis, where we look at all of the inputs and all of the outputs from every process step, all through the product life cycle, from extracting material from the ground until there's nothing left that's useful. With our life cycle modeling, we look at all of the impacts of each step. What you can see here is that there's a lot of blue on this chart. The fact that it's a significant fraction of all of the impacts is another reason why we're very interested in maintaining it. You can also see that the aluminum the green is another significant contributor, and so that explains why I'm not so happy about having it lost during the processing. And just to complete the life cycle picture, What this shows is the total life cycle energy balance for running a vehicle from manufacturing it through running. I can't remember exactly how many miles we've assumed that it's either 100 or 150,000 mile lifetime. And what you can see is that yellow or orange part on the top represents the energy that's used during the life cycle, during the operation phase of the vehicle. And so the blue, which is the manufacturing energy for the vehicle, and the lighter blue is the battery, are significant, but the main contributors to total energy use are the vehicle use phase, whether it's in the form of electricity or fuel. You can see that the total energy for the electric vehicle is considerably less than the life cycle energy for the conventional internal combustion engine vehicle, even though producing the vehicle does use somewhat more energy. What this chart shows is what some of the scarce materials that are used in an EV battery look like. And what you can see on the, this is assuming a battery that's about as big as in a Chevy Bolt or that sized car. And what I've done is compared the total US and world reserves to the number of cars that you could make using those, using that material. And what you can see is that for the amount of reserves that the US has in cobalt and nickel in particular, the number of vehicles that you could actually supply with their batteries with domestic raw material is considerably less than the total number of vehicles that we produce in any one year. The US production of vehicles is somewhere on the order of 16 million cars per year, and we could only make 8 million with the cobalt that we actually have in US reserves. So that pretty much says we're going to be importing material. We can also get some back from recycling, but unfortunately that's not going to be a big help for a while. And the reason for that is that the batteries last a long time and growth is rapid. So if you assume some demand curve like that blue one, the amount of material you could get back if you recycled everything that was produced 10 years earlier is the black curve, and the black curve is much smaller than the blue curve. And the other key piece on this is that when you make batteries, there's some scrap in the production process, and that scrap is available immediately, and new plants like we're building now have a lot of scrap. So if you assume that there's 20% scrap material on that, from that blue production curve, you get the red curve, and that's bigger than the black curves. What we've learned from our award-winning Everbat model is that the revenues that are available from recovering scrap are in fact greater than the revenues that you can get from recycling of spent cells, because a lot of the material is doesn't have all of the different components included in it, and so you can get more of the cathode scrap, more of the cathode material back from cathode scrap than you could from spent batteries. And so recovering scrap is likely to be a very profitable activity for recyclers. I just want to end by saying a little bit about the technical accomplishments that the center has achieved in its first almost 3 years of operation. Most importantly, we have recovered usable cathode material that behaves quite well. We have about 40 papers that have been submitted and accepted in journals by scientists in the center. There are about 20 patents that are in the process of being approved. And we have laboratory space ready to collaborate with other institutions when we're allowed to go back into the lab and have visitors. And we did have an industry collaboration day at the end of 2019, and we were planning on having another one. The idea of that being that we're not going to get anywhere if industry doesn't understand and approve of what we're doing. And so we had a lot of interchange, industry and other academic and lab institutions. So what we still need to do is we still have to figure out how to keep the batteries in the US, and that perhaps by having an economical recycling process available here, that'll do it. We also want to be able to make sure that the recovered materials behave as well as new ones do. We need industry buy-in, and the last thing is we want to make sure that some of the processes that we're developing will be applicable when there are new battery chemistry. We're not assuming that lithium-ion is the be-all and end-all, and there are exciting new technologies in the works. I've included in the document some resources, including the supply chain report that came out of the White House in June. We had significant input to that report. This slide shows some of the recent papers that we've published to provide information about the work we've been doing at the center. And finally, I just want to thank our sponsors at the Department of Energy. The Vehicle Technologies Office has been funding this work, and we're very grateful to them. Our sponsors on the battery side are Sam Gillard and Dave Howell, and Margaret Smith has been very, very interested in the Second Life battery information. And thank you all. I'm happy to answer questions.